to the cloud. Okay, so, all right. So last day, we won't do a review, but I do just want to highlight the things that we talked about, so hopefully they'll kind of jog your memory. But it was just on Tuesday, so so hopefully it's okay to just jump right in. We talked about real numbers and their properties, right? So things like the commutative property, we talked about the distributive property, right? That we can distribute across the brackets. We talked about, just mute you there, Tisha. We talked about negatives, right? How negatives behave, and we'll use that again today, right? And well, forever. But then we also talked about fractions, right? So we talked about fractions. We talked about, no worries. We talked about how do we multiply and divide fractions, right? That's a kind of easier than adding or subtracting fractions. If we're adding or subtracting fractions, we have to have that common denominator. And we looked at a trick for getting that common denominator. And of course, we're going to be dealing with fractions again today. And so I'm not going to spend time on an example here because it's going to come up in just a little bit. And then we talked about sets, and we got into some intervals, not really, but that's where we're picking up today. So sets and intervals, and that's kind of where we ended last day. So I'll say intervals continued. Oops, continues. Well, that still works, but I'll do continued. Okay, so for intervals, right, we left off and we were talking about, okay, well, there are closed intervals or open intervals, right, meaning that the endpoints are either inclusive or exclusive, and we had a couple of different ways of showing it, right? We can show it using inequalities, right? And so we had the less than or equal to versus the less than, for example. So we talked about, we have open, or closed, I'll rewrite that. Open or closed intervals, right? So open, in our case, would mean kind of exclusive of the endpoints, exclusive of endpoints, and then closed intervals would be inclusive of endpoints. So on a number line, right, on a number line, it would look something like, so we've got our number line here and our number line here. We said that to indicate an open interval, right, or an open endpoint, we would just do an open dot, right, versus a closed dot for the closed endpoint. For the inequalities, right, if it's an open dot, right, if we kind of cascade down, right, we would use the less than or greater than signs. If it's a closed dot, we would use the less than or equal to or greater than and equal to. And then finally, as a point, or sorry, that's not what I meant. As an interval, well, the interval would have round brackets, whereas if you have a closed interval, you have these square brackets. And then we can do a combination of these as we saw in the handout. So if you've got the handout from last day, problems of fractions, oops. Right, we've got so the open interval, right? So the round bracket interval, we can use Sept builder notation, right? And notice that it just has the less than sign, so not less than or equal to. And we've got the round, the open dots. And we can do a combination, so we can do a round bracket around A, meaning so it's not inclusive of A, but it is inclusive of B, right? If it's got the square bracket on B. One thing to notice that we didn't talk about last day was if we're dealing with infinity as an endpoint, then we have to use a round bracket, right? And how we indicate it is we just let the arrow keep going, and then we do a little arrow if it just keeps going. In fact, I would probably put, and it's not terribly important, but I would have arrows going to the left as well. Okay. And so here, just as a little note, the reason we can't have a square bracket around infinity or negative infinity is because infinity is not a number. So that means that we can't include it in our interval, right? We can get close to infinity. In fact, we can get, really, really close to infinity, or I don't know, depending on how you think about infinity. We can keep going and going and going and never get there. And so that's why we can't be inclusive. So infinity is not a number. Infinity is more like a state of mind. So, or like an idea. And so since infinity, oops, I'll do since plus minus infinity, right, to indicate either one. No such thing as a set infinity. That's right. Yeah, so there are infinite sets, but no infinity. Infinity is not a number. So good. So since plus or minus infinity, so either in the positive or the negative direction, is not a number, we must always use round brackets around infinity in an interval. Right? We must always use round brackets around either plus or minus infinity. It's always lopsided there. In our interval, I'll put in brackets, must be exclusive, of infinity, plus minus infinity again. Okay. So that's just something to keep in mind. But you can do a combination of these things, right? And so there are, three different ways that we can show the exact same information, right? If we've got this interval, we can use Sept notation, so the Sept builder notation to talk about the interval itself, or we can graph the interval. So let's just get a little warm up in and say, I want you to express the following. So example. Express in terms of inequalities and just to show off with set builder notation. Right, from last day. And then graph the interval. Then graph the interval on the number line. So the first one we're going to do is round bracket -3 up to 0 round bracket. Then we're going to do square bracket 2 up to 8 round bracket. And then we're going to do square bracket 2 up to infinity round bracket, just like we talked about. Okay. Noticing the round bracket versus the square brackets. So we'll start with the set builder notation just because it's a little bit yucky, and then we'll end on a high note with the graph on the number line. I'm going to move these over just a bit. So starting with this first one, so set builder notation, remember we start with these curly brackets, and then we're talking about just any x in general, right? So this is a pretty default setup for if you're writing set builder notation is you start with your x. So I'm talking about any x that satisfies this criteria. So such that, remember that vertical bar we read as such that, and then here is where I'm going to put my my interval in terms of inequalities. And so I want x to be between -3 and 0. So what I've got is I'm going to put x in the middle, and then from -3 to 0. Okay. Notice that, right, these round brackets result in a less than, right, not less than or equal to. That would be a square bracket, right? So what I'm saying is x has to be between -3 and 0. You always want to make sure that the way or the order that you're writing this interval makes sense. There is no interval from 0 to -3 because it doesn't go that way, right? X has to be, unless you change the inequalities, then fine. All right. How about in terms of our graph, right? So here, I'll draw my number line, and somewhere on here I'll put -3 and I'll put 0, doesn't matter where, right? We're just visualizing things. And then to show that it's not inclusive of either of these points, I'll do open dot, and then all the values in between. So how about the set builder notation for the other one, for the next one? So it starts the same way, right? Curly bracket, x such that, and then again, x is between these two numbers. So I'm just gonna write x in the middle here. X is gonna be between 2, but remembering that it's gonna be inclusive of 2, so it's gonna be less than or equal to x, depending on how you want to read it. And then up to 8, but not including 8, so then I'll just leave that inequality as it is. So how you would read this, right, is not that natural, right? It would be 2 has to be less than or equal to x, which has to be less than 8. Okay? You would probably want to talk about x being greater than or equal to 2, and x has to be less than 8 because we want to talk about x, and that's fine. Just as long as you kind of keep track of how you're reading it, but this is probably the easiest way to just be able to do all these inequalities. On our number line, so here we are back on our number line, I'll put 2 and 8 on here. And I'm going to do a closed dot at 2 because it's inclusive of 2. And open dot at 8 because it doesn't, it goes very, very close to 8, but not to 8. Okay. So, if we go on to the next one, right, we haven't talked about infinity in terms of our inequalities especially, right? But if we have a look at these two that we just did, or the one that we just did versus this one, the only thing that changes is that 8 becomes infinity, right? And if you take kind of a sneak peek at these default ones that we had, right, we'll be able to kind of get to what we need to do. But so it's going to look like, so it's going to look a lot like the one we just did, right? It's a set, well, that was a nasty set. There. The set of x such that, and so the 2 is still inclusive, so I'm going to just keep writing like I did here. 2 is less than or equal to x, right? But then because it's just going to go to infinity, I don't need to specify that. In fact, I shouldn't, just to keep it nice and clean. So that's where I'm going to end this, right? So how this reads, like I said, it's not very organic, right? So we would read this as 2 is less than or equal to x. Well, usually if we're talking about x, we want to know, okay, x has to be greater than or equal to 2, right? So we can reverse these. So however you want to write it, or we can do x such that x is greater than or equal to 2. It doesn't matter. Right? As long as the inequality is facing the x the right way, then it doesn't matter. Okay? But I do like how similar these look, right? And so that's why I would just stick with this notation. But for reading, this one reads much nicer. Okay? And then if I do my number line, here I am at 2. So it includes 2 again. So I'm going to do a filled in dot. And then just to indicate that it's going to keep going and going and going to infinity, I'm going to draw my arrow to the right. So, okay. Good. So that's kind of it for intervals for now. Let's talk about the absolute value. So I'm not sure if you guys have a lot of experience with the absolute value, but it's really not that bad. It's just a function. Same last situation with a notation like x is greater than or equal to 2 in the set of real numbers. Yeah, that would be valid too. So Avon said you could have something like you could add on here, let's see here, scoot this down, right? Or you can have something like x is any x such that x is greater than or equal to 2 x in the set of real numbers. But for us, we're kind of skipping that, but it is valid. it's just saying X can be any number, not just a whole number, for example. And make this a little bit clearer. But we just kind of, we drop this one because we're lazy. But that is valid for sure. Okay, so the absolute value, oh, well, then you had a good previous teacher. So Bon says one of his previous teachers pounded that into his head, and so that's very good. Was it Satoshi by any chance? He's very thorough. No. You'd remember if it was Satoshi. He's great. But yeah, he's very, very thorough, and that's really good. So I don't suggest that you lose that, but for us, set builder notation is hard enough. So I just want to keep it simple. Okay, so the absolute value. The absolute value basically takes any number and makes it positive. So it turns it into the positive value. So if you have a -8, for example, the absolute value of -8 is just 8. So we'll talk about the background of what's going on there. But what you need to remember is when you see the absolute value, and we use these vertical lines around a value to indicate the absolute value. And so then where your head needs to go is, okay, I just dropped the negative, right? I just dropped the negative. We'll talk a little bit about why that is. What's fun about the absolute value is that it's a function. We haven't talked about functions yet, but we will, of course. And it's a piecewise function. So it's the first time that we'll see a piecewise function. So it's kind of a nice place to kind of get started with functions. So it'll come back, but what happens is it behaves differently. So the output behaves differently depending on what's inside here, right? So if A is positive, it'll just give you A. If A is negative, right? So if you've got a negative number in here, it actually takes the negative of that negative number, which makes it positive, right? And so the absolute value is denoted by, I shouldn't say 2, by vertical bars around a value. Okay. So it looks like this. And so what's kind of cool is the absolute value function, oops, the absolute value function is a piecewise function. Meaning it behaves differently depending on what the input is. And you know what I'm going to say here? The absolute value is denoted by vertical bars around a value. I'm going to call it the input, just to get in the groove of functions later. So the absolute value function is a piecewise function, meaning it behaves differently depending on the input. Okay. So depending on what value we plug in, so if we think about our number line here, our real number line, we've got 0 here. So for these guys, for 0 onwards, right, the input A is positive, which means that, so if it's 0 or greater, right, it's positive. And so the absolute value of A is just A. Okay? Just as a little glimpse here, let's do, well, let's do 8. Right? The absolute value of 8 is just 8. It gets different here. So not including 0, because 0 was already handled on the right-hand side, right? But any values that are negative, right? So here, the input A is negative. So let's say we have negative 8. What happens is the absolute value function of negative, or sorry, the absolute value of A is the negative of A. But in this case, if we have negative 8, then we get negative 8. Right? Negative of negative from last day, we know is just positive 8. So that's how it becomes positive. But that doesn't really matter, but it's a good exercise at looking at piecewise functions and how they behave differently, and just kind of a nice introduction. But as long as what you're taking away from this is, okay, if I see these vertical bars around something, I just take the positive version of it. Okay, so if you just have to evaluate, and we'll just do 2 briefly here, the absolute value of 100, and I should probably make my bars a little bit distinguishable from my absolute values, or my 100, or the absolute value of negative 73. Well, the absolute value of 100, well, 100 is positive, so it's just 100. The absolute value of negative 73 is just going to be 73, right? Because we just dropped the negative. You don't have to go through the steps of taking the negative of the negative, although if you can, if you want to. 73. Trying to see if there's an absolute value button on here. You don't really need it, but it might be cool to know. I don't see one though. So some calculators might have an absolute value button, but you don't need it because you just drop the negative. Okay, so there are some things that we need to know about the absolute value. So there are properties of the absolute value that we should be aware of and be able to use. First one is not so bad. So once you've taken the absolute value, the result will be greater than or equal to 0. So if you've got A as, or 0 as your input, A, it'll give you 0. So that's why it can include 0, but it will always just give you a positive value. Fine. What we saw up here, right? It doesn't matter if I do the input of 8 or the input of negative 8, the result is 8 positive either way, right? And so that's what this is saying here, is that the absolute value of A is going to be the same as the absolute value of negative A. So it doesn't matter. What's fun about the absolute value is if you're multiplying, you're allowed to split up the absolute value symbol, right? And so if you've got A times B and then the absolute value of that it will be equivalent to the absolute value of A times the absolute value of B. Whereas later on, we'll see down here, if you're adding or subtracting, it'll behave differently. So it's only for multiplication and division that you can split off the absolute value symbol and still have an equivalent statement. For addition or subtraction, it'll be a little bit different. So if you just kind of consider, well, I guess they've got this example here. So there's all we can say is that the absolute value of A plus B is going to be less than or equal to. So there are some very rare cases where it's going to maybe be equal to, but mostly it's going to be less than the absolute value of A plus the absolute value of B. So if we think about things like -3 plus 5, well, -3 plus 5 puts me at 2. The absolute value of 2 is 2. So then if I think about the absolute value of -3, well, that's 3, plus the absolute value of 5, that's 5. So 3 plus 5 is 8. So now I'm looking at 2 is less than or equal to 8, which is true, right? But that's as far as we're going to go here. So one thing that I want to highlight here is these two are good to keep in mind, right? If you're multiplying or dividing, it might be useful to know that you can just bring the absolute value sign in there. I want you to develop kind of mental stoppers if you're adding or subtracting, right? Because you don't need to memorize this. In fact, I would say don't memorize this. But remember that it exists, right? So remember that there is a thing that you can look up later to kind of say, oh, okay, if I'm adding or subtracting in there, then there's something special going on, and then you can just kind of look it up and go from there and play it safe. Okay. So absolute values are usually used for distances between 2 points. And so we use absolute values. We use them in other things too, but we use absolute values to find distances between 2 points. Oops. So we've got this little So if you've got 2 points A and B, and what I'm going to assume is that A is less than B, right? Then the distance between any A and B is going to be the absolute value of B minus A. So we can start and think about these things like, okay, if I ask you the distance between 4 and 10, well, what you're going to do in your mind is say, okay, well, 10 minus 4 is 6, so the distance must be 6. But then we have to think a little bit harder if I say, okay, well, what's the distance between -2 and 10? Well, between -2 and 10, you would say, okay, well, from 0 to 10, it's 10. And then from 0 to -2, it's 2. So I need to take that into account, right? And so the total distance would be 12. But by using this, it'll work every time. So regardless of if you're talking about negative points or positive points. So it just says that the distance between A and B, so we've got this little D operator here, D of A and B is the absolute value of B minus A. So as a little exercise, find the distance between 2 and 7 or 17, let's say. Doesn't matter. But it's what I have in my notes. -3 and 21, so very similar to that scenario that we were just talking about. And to get a little bit, I don't want to say mean, but mean, between -3/10 and 11/8. Fractions, come on. Good thing we know how to deal with fractions, right? So, we'll start with the first one. The distance between 2 and 17. And notice that I've always put the kind of the leftmost number on a number line first, and then the rightmost. Don't think it matters, but just to play it safe. So the distance between 2 and 17, well, that's going to be the absolute value of 17 minus 2, putting me at 15. Right? And the absolute value of 15 is just 15, so I'm just going to skip straight there. Right? If I have a positive value, I don't need to worry about it. How about the next one? The distance between -3 and 21. So this is one of those where we've got some on the negative side, right? But that's still distance. And so what we have is we take 21 minus -3, and then take the absolute value. So we've got 21 plus 3, right? And then the absolute value. So 21 plus 3 is 24. Absolute value of 24 is just 24. Gearing up for the more work, right? With the fractions, there's still a distance here, so we can find it. The distance between -3/10 and 11/8, we'll map it out here, but we want the absolute value, and I'll take up 2 lines here just to make it nice and neat, or neater looking. So we're going to do 11/8 minus -3/10. Notice how I'm putting the brackets around just to show that, okay, I've got a negative and a negative, just so my eye doesn't skip around and think it's only one negative, because it should turn into a positive, right? So I just want to kind of give my brain a little heads up there. Okay, so I don't know if you guys can see, but there's these page breaks that I'm dealing with. So what I'm going to do is I'm going to rewrite this and also give myself more space. I'm going to rewrite it over here. So I've got the absolute value of 11/8 minus, so I'm just rewriting it because I ran out of room, equals, well, I can simplify it a little bit, right? I can rewrite it as 11/8 plus 3/10. So let's do that. Keeping those absolute value symbols all the way through. You don't want to drop them, even though it might be tempting sometimes to just kind of, I'll deal with that later. But then oftentimes you forget to deal with it later. So just always keep everything, even if it's annoying. 11/8 plus 3/10. So now I'm adding fractions, which we talked about last day. So I promised that we would get some practice here with our fractions. Here we are. Okay. So I need a common denominator, right? 8 and 10, they're not common. And so there's lots of different ways that you can do it. You can use your fancy ways if you want to find the greatest common factor, that's fine. I think that's a lot of work. So mine is not as pretty as that. But we need to find a common factor between 8 and 10, and we talked about this last day. Yeah, you could use 40, but I'm going to stick with my foolproof method of just using 8 times 10. Right? So you could get fancy and use 40, that's fine, but I'm going to use 8 times 10, which means on this first term, I have to multiply by 10 over 10. 10 over 10 is 1, right? So I'm multiplying by a convenient value of 1. And so basically what I'm looking at is I'm looking over here on this term, and then I'm glancing over here and multiplying by 10 over 10. Then I move over to this side here, and I do the same thing. I glance over here, and I multiply this second term by 8 over 8. And then that way I've forced both of my denominators to be 80. So what I've got here is I've got 11 over 8 times 10 over 10, right? That's just multiplying fractions, so that's easy. We just multiply across. Plus 3 over 10 times 8 over 8. So we're going to do this a lot. So if there's anything about it that doesn't make sense, I know this can be kind of tricky for a lot of people. So, so just throw the questions out there if you have any, or if you want to sit on it for a little bit longer, that's okay. But just make sure that this really makes sense to you. Okay? So now I've got the absolute value of 11 times 10. It's 110 over 8 times 10 is 80, plus 3 times 8, 24, over 10 times 8, which is 80. So now I have that nice common denominator of 80. Right? So now that I have this common denominator, now I'm allowed to add these. And remember, you just add the top. So you add the numerators, and then you just use that common denominator as the denominator. So it's a little bit different from the multiplication. But so you get 110 plus 24 is 134 over 80. And the absolute value of that is just, because 134 over 80 is positive, we can just drop the absolute value. And so we get 134 over 80. You can simplify it, but you don't have to. Here, I would say you're done. I'm not that picky, but if you have kind of one of these calculators, 134 over 80 it'll just give you the reduced, so the simplified form. So if you have one, so then you could say or 67 over 40 if you want to, but not necessary. I think they have these calculators in the bookstore, but and even online or whatever. But any calculator will be fine. But it's nice because these ones they're usually like the engineering ones, so so they always give you the exact answer and simplified, which is kind of cheating, but makes it easier. Good. So if we do that on our calculator, which is approximately equal to, right, as soon as I'm talking about a decimal, so I don't know if you can see there, I do approximately equal to 1.675. Nice. So either way, we should get to 1.675. Okay. Good. Nice. All right. Any questions before we start the next section? All right. Then I'll put it on a fresh page here. And we'll start 1.2, which is exponents and radicals. Radicals are just roots, right? Square roots. And then we'll talk about different roots, but that's later. Okay. So just as a little refresher on exponents, right? Because we need to be really good at dealing with exponents. Oh, and before I kind of get going in this section, so usually what I do is I want to take our time in chapter 1 and really develop these fundamental things that we kind of should be bringing into the course, but depending on where you're coming from, like if you're straight out of high school, you probably had a weird end of semester in your grade 12 year, so things probably got weird in math too. Or if it's been a while, right, you've been working and then now you're back at school. Either way, a lot of this stuff isn't that fresh for a lot of us. So that's why I want to spend our time and go through chapter 1 so that we're all on the same page. And I think I warned you about that last day, is that it could get kind of boring if all this is all top notch for you. But for those of you who need a refresher, it's really important. So, and then we'll all be on the same page after. But usually chapter 1 takes, you know, the first 2 or 3 weeks or so. So exponents are when we write things like a to the power of n, right? So here we've got the nth power. So we call it the power, or n is the exponent. So exponent or power if you want. So if I have a times a times a times a times a n times, then I can rewrite it and summarize it as a to the power of n, right, where n is the power or the exponent. A is the base, right, and so we'll have to pay attention to the base, because as we'll see later, we'll only be able to combine like bases. Okay, so it's just a way of summarizing values. So if we have something like 8 times 8 times 8 times 8 times 8 times 8, I can rewrite this as, well, let's just kind of summarize this. So my base is 8 and my power is 1, 2, 3, 4, 5, 6. So I can rewrite this as 8 to the power of 6. Okay. We can also have negative exponents. So negative exponents, and I'll cut that little are special because it bumps you down, or it bumps that base down to the denominator, right? So here, if I've got a negative exponent, then that's the same as, so a to the negative n is the same as 1 over a to the power of n, right? Notice that by bumping it, I say bumping it down to the denominator, then we lose that negative because that's what the negative is saying, that it's in the denominator. Okay. Another kind of fun thing is that anything to the power of 0 is just going to be 1. So Unlike, 4 times 0, that's just 0, right? But 4 to the power of 0 is just 1. Okay? As long as, of course, the base is not 0. 0 to the power of 0 is just 0. Okay? So as long as the base is not 0, any base to the power of 0, any base to the power of 0 is 1. Okay. So here, this little guy, right? Often I move this way to kind of consolidate everything on the same level, right? So if I'm able to rewrite something in the denominator as if it's up here in the numerator, right, that'll make it easier to simplify things. But in order to simplify things, we need to have the laws of exponents. So here are the laws of exponents. Oops. So the laws of exponents, make it a little bit bigger here. So there are a lot of laws of exponents, and I do expect you to have these probably not memorized, but memorized to begin with, but then just be able to use them fluently, right? And so if you see an exponent, you'll know how to deal with it, right? And it just has to be second nature. And we'll do a couple of examples just to make sure that we've got it, right? What's nice is that they all kind of go hand in hand and they're all related somehow. But okay, we want to pay attention to the bases that are given here, right? If it says that it has to be the same base, then it only applies if you have the same base, of course. So we'll start kind of slow and say a to the power of m times a to the power of n. We have the same base a, meaning that we can combine these to just have one power. So we have a to the power of m plus n. So if we're multiplying the bases, we would add the exponents, and that's how we would simplify. And that's just a rule that we need to remember. If we're dividing, I'll show you, it's very similar, right? If you have a to the power of m over a to the power of n, that's going to be the same as a to the power of m minus n. Okay? And I'll show you why. So if you've got a to the power of m over a to the power of n, okay, what I can do from that first rule that we established here, right? If I've got a to the power of n in the denominator, I can bring that upstairs, right, by writing a to the negative n. So what I can do is I can rewrite this as equals a to the power of m times a to the negative n. Now, I'm multiplying two values with the same base, right? And so what I can do from that first law is I just add these up. So this is going to be a to the power of m plus negative n, which of course is just a to the m minus n, which is exactly what it says it is here. N. So if they're being multiplied up here, then they're still going to multiply once you remove those brackets. I want to move the chat a bit. Good. So if you've got two bases being multiplied inside the brackets, and then those are all to the power of n, you have to be really careful that you distribute the n onto both of these terms. And what we'll emphasize later on in the course is that you need to put that n on both things inside the bracket, right? And it only works if we're multiplying or dividing, as we see in the next one here, right? And so it only works if we're multiplying or dividing, just like the absolute value bracket, right? So if you're multiplying or dividing, you're safe. You can bring it inside. You can bring the power inside, but it has to go on both the values inside. So those, there's not a lot to do with. But let's have a look at number 6. So law number 6 says that if you have a over b to the power of negative n, that's going to be the same as b over a to the power of n. So let's just have a look at that and see and convince ourselves that we know why. So we have a over b to the power of negative n. And I'm just going to tease it out until I get to that final end stage that we've got in the laws. And I would say instead of, so I don't want you to memorize these things, right? So far, we only really need to know how to multiply bases, the same bases, to combine their exponents, and how to bring that exponent down or up from the denominator, right? So there's only 2 key players that we need, and then everything else will fall out of there. Okay, so it says a to the negative n over b to the